indeterminate cases, we know how to deal with the ratios. Let me refresh your memory on how to deal with the difference. Okay, so let's take a look at an example. I hope I can find one. Quickly. We had these, they should not be in this section anymore. We had them in at the very beginning when we studied limits. Well, I can find one quickly, or I can go back. It's not, I don't see any in this section. Oh, no. It's looking, still looking. I mean, there is one, but it's not what I'm really looking for. So yeah, that's fine. 55. Limit as x approaches 0 from the right. Careful, they are omitting the parenthesis. This is incorrect. Okay, so this is incorrect. What they omitted parentheses. I don't know if in the online version, but here the parentheses are missing. This is incorrect on 55. Okay, good. So I was looking for an example like this. So this is what we obtained here. This is how we start with here. So I know the graph of this, and this has to be embedded in our system. We know that, right? So this is the graph of 1 over x. 0 from the right, this piece approaches infinity. 0 from the right. So this is 1 over x. What about the graph of tangent? Okay, so the graph of tangent is this. Of course, with negative pi over 2 and pi over 2. X equals negative pi over 2 and x equals pi over 2. But this is 1 over tangent. So the denominator approaches 0 from the right. It's the same thing, same idea. So this approaches infinity. So this is the case that I'm trying to discuss, the difference. Let me see if you can see. So it's infinity minus infinity. Again, in an indeterminate case, you cannot conclude, you cannot say anything about it. So we'll continue. So limit as x approaches 0 from the right. I'm going to find the least common denominator. Can anyone give us the least common denominator?
Pi is 1 over tan infinity again?
Because, see, at x approaches 0 from the right, tangent, this is tangent, is 0. 1
Does it
over
not
0.
matter that it's 1 over tangent?
1 over 0. Yes. 1 over 0 is this situation. So tangent approaches 0. But 1 over 0 is similar to 1 over 0 here. Approaches infinity.
Okay.
If you have any doubts, put this function with radians. Make sure, put this function with radians in the graphing calculator and approach 0 from the right with 0.3, with 0.2, with 0.1, and you will see it will blow up. Since you're asking, very good question. Okay, so if you're not convinced, so just, no, I didn't mean that. So in y equals, okay, so I put a 1 over, so you can put tangent x. Nope, I didn't mean that. I didn't mean that. I meant this. Left parenthesis, tangent x, and close again. No, I didn't mean twice. And put power -1 on it. That's what it means, 1 over tangent. And when you go to the table and you put in, let's say it's from the right, so 0.3, 0.2, 0.000001, boom! Look at this. Okay, so the closer you get to 0, the higher the value. So they're infinity, it's infinity minus infinity. If luckily this would have been positive, I would have had the answer infinity, I would have been done by now. But that's not the case. Okay then, so what is the least common denominator?
X times tan x.
Very good. So then I have here tangent x and minus x. I'm hoping for 0 over 0 or infinity over infinity. So this is 0, this is 0, yay! This is 0, this is 0, yay! Wonderful. So infinity minus infinity with a simple algebraic manipulation, if you want, changed into something I'm very happy to see. So then limit Sx approaches 0 from the right.
I have a quick question.
Yes?
If infinity minus infinity is one of the 7 indeterminate cases, do you really need to check a second time that it's 0 over 0? Because aren't all indeterminate cases L'Hopital's rule, or only 0 over 0?
L'Hopital's rule is applicable only if in the case of 0 over 0 or infinity over infinity.
Oh, sorry. I have that on my paper too. I don't know why.
That's okay. No other case, all the other cases have to be changed into these two so that L'Hopital's rule is applicable if we can. Yes. Is that better, Katie?
Yeah, thank you.
Thank you. Okay. So then I have secant squared minus 1. This is, careful, it's a product rule. So the first function prime is 1, tangent x, plus x times secant squared x. Okay, now I check again. This is 1 minus 1. I don't like it, but this is what it is. Let's see, 0 from the right, this is 0, and this is 1. Okay, I'll try again. Secant squared, 2, secant x, times secant prime, which is secant x times tangent x. Let's see the denominator. I know, what time is it? Oh, okay, I have 2 more minutes. You can leave after 2 more minutes if that's what you want to do. Okay, tangent x is secant squared. And this is x prime is 1, so this is secant squared, plus x times secant squared prime, 2, secant x, tangent x. Okay, this is 1. This is 1. This, I don't care, is 0. This is 1. This is 1, but this is 0. 0 over 2 is 0.